There are 7 parts to Theorem 2.2. I'm going to prove the 4th part. It's a pretty standard proof, but all of these proofs should be done in about the same way. So the 4th part says that if you have integers a, b, and c, and you have an if statement, so we have 3 integers a, b, and c, and I know that if a divides b and b divides c, then I can conclude that a divides c. So for this proof, this is going to be a straightforward, very deductive proof. I'm going to start with this if statement here. So a divides b would give us, so if we have a divides b, then we can say b equals ax, and I could put a plus 0 if I want, a remainder of 0, where x is an integer. We have a remainder of 0, a quotient of x. I'm going to do the same thing with b divides c. So if b divides c, then c equals by, where y is some random integer. Okay, and I'm just using the definition of divisible. It goes into it evenly. We have a remainder of 0. So I'm going to start with this equation right here. I'm going to say c equals b times y. Well, I have an equation right up above it for b. b equals ax. So I'm going to substitute ax in for b. So I'm going to say c equals ax times y. Now, this is a times x, the quantity a times x times y, but multiplication is associative, so I can actually move my parentheses from around ax onto around xy. So I could say that this is c equals a times xy. Now what's important to note is that xy is an integer. And I know that because both x and y are integers as previously stated. So xy is an integer, and I have c equals a times some integer xy. That goes directly to saying that a divides c, and it's actually finished with that.